Hello, good morning everyone. So, welcome to another Math Club talk. Today with us we have Samadrita Bhattacharya of uh, Bachelor second year, and she is presenting a talk on introduction to Causal Inference. Her interest areas are statistics, probability.
So let's start. I will first introduce the topic and give a bit of motivation why we study first. For this, I have an example which is commonly known as a simple study. It was introduced by Edward Simpson in 1950. So, what we have here is a group of people, all of whom were affected by the same disease, and they were also from drugs, which some of them took and some of them didn't. So their response to what the drug or not is recorded here, segregated by sex. So what we find in this here is that we see in men 87% recovered without the drug, while 93% recovered with. In case of women, 69% recovered without it, and 17% recovered, which would ideally suggest that a drug is actually effective in the entire population. It's affecting both men and women. But if we look at the entire data, we see that 83% people recovered without the drug, and 70% recovered. Now, this inference is very paradoxical. So, when we're looking at the whole data set, you're getting one sort of answer, and you're looking at the data set separated by gender, you're getting some different answer. This seems very paradoxical, and I'll explain in this slide. So, you see that we make these following observations from the data. Women have a lesser recovery in gender. So, even in the lab, women have a lesser recovery than men. What else can we say? We say women are more likely to opt for the drug. We see here that a lot more women opted for the drug than men. And the third point is that women taking the drug also have a lower recovery rate than men not taking the drug. We can look and see that men not taking the drug have a higher recovery than women. This would mean that there is some sort of correlation between your gender and your recovery. And so that estrogen hinders the effect, leading to no recovery rate. With this and the previous observation, we are able to conclude that the correlation between gender and the recovery is in fact causal. What do you mean by causal? It means that whether it's a man or a woman, it will affect your recovery, and thus it is affecting the study of the data that we have. So in this case, it is in fact better to study both the genders separately to arrive at the conclusion that this drug is indeed. Another example in the similar situation is that this drug, we have a second drug now, and this drug basically works by lowering the blood pressure of the patient. But it also has a slight toxic effect. What we see here again is that we look at the recovery rates created by the low and high BP. We see that the drug is we see that in the combined data set of the drug. Sorry. In the combined data set of the drug and the subjects that not, which is again a paradox. Here the explanation that arises is that it is not the BP that is affecting the drug, but the drug that is affecting the BP. So in this case, you don't really need to make subsets of the data based on the study. So here it makes no sense to look at the data. When do we look at the subsets? When do we not? Questions like these are answered using causation. So now I'm going to start with a very simple definition of causation. Okay, before we go into that, there's two main approaches to causal inference. One is using interventions and look calculus, and the second counterfactual. So what are counterfactuals? Counterfactual is the kind of statement we commonly make. Like, say I forgot to take an umbrella. I go out and it starts to rain. And I say, oh damn, I should have taken it. So things like that. So what is the probability that if I had in fact taken the umbrella, it would have still rained. So causal inference tries, counter try to get causal inference using trying to find the probability of change like that. On the other hand, you have what it does is, I'll talk about it. This one tries to identify situations where you can look at causal inference. So, see how causal assumptions are very important. Like in the example I showed, the assumption that estrogen hinders the drug was very important in making the causal inference. So I will start with a brief introduction to look at, which is the main model, right? And then I'll give a brief on that. So first we start with a very basic definition of model, which is that a variable is if y depends on x, what is that? This is a very simple definition. This is the most natural one that comes to our mind. So now we move on and try to understand what is structural causal model. It is the simplest and most natural way in which we express our causal assumptions and ideas to understand data. So, and then visualize using directed assignment. So, what do we mean by developing causation on a? So this what that if a variable x is a direct causal path, then we draw a directed edge from x. And in this case, we call x the parent of y and y the child. Like in this graph now, so there is x is the parent of y, y is the parent. And because x is basically ancestor and z is a descendant of x. What do ancestor and descendant mean in more general terms? If we have a directed path from a variable x to another variable z, then z is the descendant and x is the ancestor. Now that we've understood how we depict it on a graph, let us understand the definition of a structural causal. So it basically contains two sets of variables. We call U exogenous variables because they are basically external to the system. I'll explain. And endogenous variables are the ones who are more interested in study. So we have a set of functions which for every variable in T, that is our endogenous variables, define a function of some exogenous variable and some endogenous variables which are called the parents. Basically in the graph we define the endogenous variables that will have arrows into that variable, they will be the parents. So that is how we define the functions. And these are just some important rules in defining an STR. That the exogenous variable does not have a parent within the model, and the endogenous variables are the descendant of at least one variable. So what do I mean by exogenous variables are external to the system? If you know the value of every exogenous variable, then you will be able to identify the entire system. Like I'll show you this example now. So this is an example of these functions, and based on this function of the. So we have four variables: ux, y, z, and these are the functions defining x, y, z, and w as indicated by the function. So, as you can see, you know all the exogenous variables. You would know ux, you would know x. If you come down to z, you know ux, you know x. You also know u, so you'll be able to define z. And then a similarly interesting. Knowing all the exogenous variables lets you know of each value of it. Now, we are usually more interested in studying the interdependencies or causal properties of the exogenous variables. So, in a lot of graphs, I'll actually not have long variables. Because often what is done is that you have a graph and you take all the external factors that might affect the value of a variable and in general call them the use of that variable and then ignore it. So,
you write fx times ux,
yes.
but then you said you know x. How do you know x?
No, I said if you know ux, then you know x by the function.
By that arrow.
Yeah. I mean, this function was used to draw this arrow because x is defined by 2 times ux.
Oh, x is to 10.
So fx is the function defining x.
Oh.
And this is another simple property of it helps us write down a joint distribution. So this is basically the joint distribution of quantity. And what we can is write it as a product of all variables dependent on the and we do it in the same side of. So now we move on. Now that we've understood exactly how to detect causation and make a definition of the CNS, discuss the three most basic causal structures which can be used to decode more complex causal structures. So I will start each of these with an example and then follow up with what the theory. So the first example, the sports engineering and so X here is a sports engineer. Y is the provision of narcotic painkillers, and Z is level. So it has been seen in a lot of variants that a person with a high tendency to sports injuries has a higher exposure to narcotic painkillers, and then often, not in all cases, but in a lot of cases, would lead to a person becoming addicted to those. What we find is that if you know that a person has been exposed to a high amount of narcotic painkillers, then knowing that they have had a sports injury in the past does not give you any extra information about whether they're a drug addict or not. So what I'm trying to say here is that the causation transferred due to a sports injury to drug addiction is completely contained in the information of whether they've had narcotic painkillers or not. So what I'm saying is that X and Z in this situation are expected to ideally have some sort of a causal dependency because X causes Y causes Z, so X must cause Z in some sense. But if you do Y, then X doesn't give us any extra information. That means condition. Yeah. So I was saying, we expect there to be some causal association between X and Z, but condition on Y actually makes them independent of. And we can formally call this causal structure a chain. So because obviously it's an entire direction. And here the
Question.
yeah.
So your claim only validated if there's no other variable like y. So if there's a y prime that is also has this kind of a structure,
Yeah.
then
I mean here I'm only working with three variables. Because when we have more complex structures like with more variables,
then also it will not be.
then
right?
I mean I'll discuss it further. But say we have another system with X, and then I will Y. So Y. Then actually we can look at this as two different parts and kind of
Right.
they're two different things.
Right.
So depending on how many variables you have and how your graph looks, you have
Here you need x and z to be dependent on other variables that are not independent of that are not dependent on each other. Otherwise,
yeah, I mean in this situation, Y is basically the only variable between X.
then it will not be independent. If x is let's say 2y and z is like 3y, then even if you condition, those will not be independent, right? You need some other variables that are independent. That are independent.
X is 2y and Y is that means your graph actually becomes independent because the arrow goes from Y to X instead of X.
Ah, I see. So how does dependent structure look like? So one-sided arrows is some sort of inequality.
No, it just means that there is a causal dependence of X. A causal dependence of Y on X. So whatever value X takes will
Determine.
and what I'm saying here is that if you know Y, it doesn't really matter what X was for you to define it.
Yes. Okay.
And obviously there might be some association, but here we're specifically talking of the association that is positive. So that is completely different. So now the second example. We have Y is smoking, X Z is that. Now smoking is known to cause lung cancer. And smoking also often leads to yellowing at the base of our nail. So here we would like to go same way. Try to understand the association between X and Z because they don't have a direct arrow saying that they are actually positive. So to study this, it's because they're caused by the same thing. They're both caused by Y. There is some dependence. But again, if we condition on Y, we can see that knowing that someone is smoker basically cuts off the dependency of lung cancer on yellow fever. Because if I know, say, some person smokes, then if you come and tell me, oh, that person has yellow fever, you're not giving me any extra information. I know this. The probability of them developing lung cancer will just depend on them smoking. It will not depend on whether they have yellow fingers or not. But if in the situation where I don't know the value of Y, and you tell me someone has yellow fingers, okay, they have yellow fingers, they're more likely to be smoking. And if they're smoking, they're more likely to be lung. That is how the analysis works in case of one. But again, knowing Y basically blocks that one. And this structure is commonly known as a pole because two outgoing arrows in the same period. And as we saw, knowing Y makes X and Z conditionally call it a condition. And in case, again, an important factor here is that only path between X and Z is Y. If there are other paths, then that will cause other paths. But here we're only talking about the simplicity. And in this case, Y is called a confound because it induces some sort of, it is a cause of both of them and it is inducing some sort of dependence where there actually is. So now my third example is balance right and exercise. So here my X is balance right, Z is exercise and Y is healthy. So we know that having a balance right makes you healthy. But I can have a great diet and still not exercise, and I can have an amazing exercise routine without health. It is possible, theoretically. What if you know that someone is healthy? Then you're more likely to okay, they have a great diet and they. So two variables that are actually independent and becoming dependent when you're conditioning on the variable. There's a common effect. So if you know the effect, then you're basically restricting what values the cause can be. If you know there was a flood in a place, you know there was some kind of soil erosion issue or something. Knowing the result causes some sort of restriction on the cause rate. But it doesn't work here. So in this case, we call it called the structure of collider because two independent variables are colliding at the same time. And conditioning on Y makes the development and Y here is obviously now these were structures. Now that we've understood where the structure causes dependence and independence, we will use this to define something called deseparation. So a deseparation is basically a way we use to define in a very complex graph which variables are independent of each. So like we saw in forks and chains, conditioning on the middle variable was causing removing the dependence, it was causing independence, so it was basically blocking the flow of dependence in that path and not conditioning on the collider. The collider by itself just makes the way. Conditioning on it instead unblocks that flow. So formally we state this paths can be blocked by a set path between variable state and C. X of variables X and Y. The path between them is said to be blocked by a set Z in the following way. So if you have a chain X or a fork such that the middle variable is a part of my chain. And if we have a variable is not a. I'm going to find deseparation as the situation where all paths between two variables are. That means in the graph there is a condition on the variables in the set Z, your X and Y become independent. So here I have an example. So the use of arguments are all face and the ones that presented in this color are dependent and the. And we can see if we want to see the dependent in y, z, and represented the pathway, we have a collider. So that means this path basically blocked by this, and as a result, z and y are independent. If we were to say condition on w for some, it would actually become different. That was deseparate. And now we move on to interventions, which are basically the very common way to study and make sense of complicated problems. So why do we use intervention? Because say you want to make a study on whether screen time is making children more violent. Why do you want to do this study? So you can understand that, okay, will cutting them off from the screen actually help them make them. So most causal studies that we do, the aim is to see whether they're effective on an interval dataset or not. So this is why interventions are very. How do we define it? We artificially take our dataset and fix the value of a particular variable at a certain level. So, and when we do that, it means that we are removing all causal dependencies. So if I fix the value, that means it doesn't really have any parents, it is randomly fixed. So I can remove all arrows ready to that value. If this is my initial graph and I run x, then I remove the arrow going to z waves. So we can call this a graph surgery because moving one. And it basically simplifies your graph. So I will show you the examples how this helps us. And okay, so this is the relation that we use to differentiate between conditioning and intervention. They appear to be the same thing. But conditioning, what happens is if you have an entire data, then conditioning is just looking at the substantive values taking that particular set. But it means that fixing the entire data set to take that value. We denote that by condition of bracket capital X values. Means we are fixing all the capital X values to that particular space. So now we go back to section 5, and I will be coming back to this example because it's very simple graph, and we use that to understand how intervention. So, like I explained in that case, the first graph, the one that I will, the male and female sub. So in that, we find X as the degree, Y as the gender variance, and Z as. We saw that gender had an effect on both the choice of treatment and the treatment. So we draw an arrow from Y to X and to Y. And treatment, in any case, always has an effect on treatment. So we always run. So, like we said there, it was actually better to study the data by condition, basically looking at males and females separately. And this example will show why that. So, if you want to find the there is a very simple formula again, right? Usually start that. So we have equal means successful recovery. Condition on the that everyone takes the treatment minus the probability. And everyone doesn't. We call this the average causal effect. So it tells you what would happen if everyone was data set then every data set did not need it. If this value is positive, that means these are values and this negative means it's not. Now I will not do this. The calculation can be done if you just take the data and fit the values. But I will say it's so like I explained, this is what we show. Find the calculus of the graph, and I'm just writing it as the general formula and I will evaluate this. So now we compare the post and pre-intervention graphs, and we look at the fact that this probability, which you technically cannot work on, like you cannot define what the intervention probability is telling, which is why we use this graph, where I find the probability of these are. it was manipulated. And we can see that in this set, because x, all the x's are the same, the probability is the same as the conditional probability of x. So we will try to find this value of the data set. And you see that after intervening, we will have two invariant equations. As which is that the distribution of y will be same in both the graphs because you're not changing any dependency, you're just removing an arrow going out of, so that is not affecting the value y needs. And now the probability of z give condition of both x and y also does not change. And this happens because, see, look at this. See that in this graph, if you knew x and y in terms of condition, the probability that z would get is the same as if x and y were fixed here. It doesn't really matter whether how x was fixed, whether it was fixed for an intervention program. It just matters that it was fixed. So the probability z is dependent on x and y will be the same. So this is invariant figure. And now this third comes from the fact that in the deseparated graph, in the manipulated graph, we saw that x, z, y is the correct. So z is belonging to, so x and y are deseparated. And because they are deseparated, you can say that in the manipulated graph, probability of y given x is the same as y. And using this, we basically take this equation, condition the whole thing on y, and write it as this. And then we use the deseparating part to write it down like in the condition on x. And because these two are the same and they're invariant, we will just remove the n because obviously P sub n is not a real model. We don't have the data for that. We have the data for our actual, the pre-intervention. So we can't find these values, but from data we can find the values of the pre-intervention. And because these two are invariant, we can write them in the form of pre-intervention case and we get this. So as we saw that we are in fact conditioning on y, which is general, and we are looking at the determinants of various elements, which means that earlier inference was in fact. The other drug, the one that affected blood pressure. So here the drug is affecting blood pressure with an arrow from x to y, and an arrow from y to z because blood pressure affected the lung. And we also have an arrow from sigma because here x does not have parents intrinsic to the one. So doing intervention is the task. So your probability does not change. You have to be the condition. So we can use these two equations and we can generalize and write it as an adjustment. Why do we call it adjustment formula? Because you're basically adjusting for variables that are transmitting association that is not positive. So we call it the adjustment formula. So here said that we're intervening on it is the conditional sums were parent things. And so yeah, this is basically the product decomposition that we discussed earlier. Because this will help us generalize our single intervention because we only intervene on one variable. This will help us generalize to multiple variables. So what we can see here is that we want to do. So what happens is that if you're intervening on some variables x for x, and you want to write the probability distribution, the joint distribution of that, just move the x1 to x and y. So yeah, because in the product, as we saw in the previous slide, you had all the variables in the model and they're there. But because you're intervening to fix those values, the xi variables take those values as probability, and you can basically remove them from the product and we get this happy. Where only the non-intervening variables show up and their effects. So if we want to find causal effect of this multiple intervention on only one particular, we can obviously just find the marginal probability sum over every other value. And we can use that value the causal effect in case of multiple interventions. This is showing how basically this is the parents of y. The basic joint distribution, not just per se. So I wrote the joint distribution as the x, and we can see that in the probability of y given its parents, in z given its parents, and we remove x with the log c. That is all about intervention. And now we move on to I'm answering this question. When does adjustment formation give us the complete process? So, like I was saying, the pathways.
So then we like intervention. We are fixing the value of x, and then we are looking at all the other values based on the value of x, right? So there's a probability of like conditional probability and the intervention probability like are they comparable? Can we compare?
You cannot actually find the intervention probability directly from data.
So, but
In the data, you don't have everyone data. So we use manipulations and invariances to reach that.
so
And yes, at the end, it comes out to some sort of condition. But yeah, you can't find the intervention probability directly.
then how do we work with
The manipulation that I created, we use the manipulation model. The one in which you don't have a intervention, so you can write down the probability as a simple condition. And when you can do that, we look at values that are invariant throughout both of the models, so that you can evaluate the conditional probability in terms of those invariants and bring them back into the intervention model, so you can actually evaluate the probability from. Yeah, so we'll answer this question, which is when exactly does the adjustment formula gives the complete process. I would say that if you have two variables and you have paths between them, then the causal, so basically these paths are either transmitting causal association or they're transmitting non-causal. If you want to complete causal effect, what you have to do is you have to block all the non-causal, which is the one natural way one. That we block all the non. And the backdoor criterion basically tells us backdoor, as when they're transmitting to an extended level. So a backdoor path is the path from x to y that transmits non-causal. How does it do that? So this basically so we are looking at the causal dependency of y and w. You can see that there are three paths dependency color. This. So this is a direct path to w. This is direct to y. Transmitting from y to w. But this path, the arrow from y to x is actually directed into x. So the association x is transmitting to y is positive, but y isn't transmitting any positive. So this would be something we call a backdoor, because yes, association is there, but it's not positive. So let me put the one x positive. So y to s instead of the backdoor. Now the backdoor criteria is a set of variables. Not a set of. So the backdoor criteria is fulfilled by a set of variables. If these variables are able to block all the backdoors. And in the situation where we're able to conditioning these set of variables is enough for you to get the causal effect of x on y. So, like in the previous diagram, we saw x, z, and s are the value of variables that we encounter in the non-causal pathway. So we can see this is a fork, this will change, and this is also. So we can condition s to block this one. and we can condition on any one of x and z to block the path, the thing. So, like I wrote down in this right now. So there are two possibilities. Sometimes what happens is that, say, x is got some sort of genetic factor which we are not able to collect data on. So that means x becomes an unmeasured variable. And in that case, we have no choice but to condition. So knowing that conditioning on any one value is enough to block your entire is actually very useful. So that was that we did. This is one benefit of the type. So we can see that to evaluate causal influence of x on y, we have this one backdoor class. This is actually block by its own because w is a correct. So this is a very simple case. But what if x is some kind of thing and w is some sort of variable that measures post-treatment pain? So we might be interested in knowing how the treatment works for people who had no pain. Because that might help you make your treatment better. What do we do with that scenario? We will have to condition. But again, the background criteria tells us that conditioning on any one of z or d would still be enough to block them. So it is so just conditioning on z, we just condition on z or whichever value have more readily available, and that will still give you a w specific positive. So that is what we call modified positive. So if you want to find the w specific positive, the causal effect of x on y, conditioning that w takes a particular value, you can still write it down as a sum over the values conditioning over z and t, and you still get the answer. This is another example. What we see is that if you're interested in finding the causal effect of x on y, then we would have to block this path. But if we block this path, what becomes interesting is the path from x to d to z to w to y will become unblocked. The z was a potato in that. So we actually have to condition. On z and to then these you don't have to condition on words together. So now moving on to this is one case where we'll see how data can be used to fool people first, and secondly understand what the front door criteria is. Now the front door criteria is sort of like a reverse thing of backward criteria. In backward criteria, we were blocking all the non-common pathways. Here we'll be basically generalizing to a scenario where you have multiple causal pathways and you can still find the causal. So here we have two groups of people arguing about whether the causal affects or not. So tobacco companies, which would obviously want to sell their cigarettes and everything, they claim that this smoking was actually people smoked because they had a natural craving to nicotine caused by some sort of genotype present in them. And the genotype also led to tar deposits forming in the lungs, which is what caused them. So they're trying to claim that the entire association between smoking and lung cancer is completely non-causal. And yeah, I will show you the data. But people against smoking claim that smoking, the genotype doesn't, obviously for fact they have to accept that the genotype exists. So even if the genotype was causing some sort of backdoor path transmitting non-causal association, they said that tar deposits were actually caused by smoke. And That is why focus is targeting causal association programming. Now, I'll show you the arguments on both of them. So this is the data method of accuracy use. So we are assuming them to be a binary variables, whether you smooth, whether you want with the start of this binary variable. I mean, obviously this is very skewed because you have 400 smokers out there using iPhone cancer and 400 PhD 100. So this is very skewed behavior. But what they're arguing is that, like they said that if you look at so we have the genotype causes genotype causes start causes cause. So they're claiming that we can condition our start causes that should block this path. And because it blocks that path, we can able to independently see whether smoking and cancer are dependent. What they're claiming here is that in both of the subsets, smoking actually so basically only 15% of smokers have lung cancer compared to 90.5%. And within each subset of the data, you have non-smokers developing cancer with more likely. Which is the subset of what having that and not having that. And the other side of it argued is that this analysis is completely wrong. Makes no sense. And what they're saying is that smoking causes tardive growth. So it makes more sense to condition smoking to see the effect of tardive growth. So they looked at the subset of smokers and non-smokers separately and saw that in either case, tar deposits increase your probability of having lung cancer within the subset of smokers and non-smokers. And within each subset, you see that non-smokers have a much less probability of having that. So that would mean that not smoking is a very obvious way to avoid that. So that was the argument. Obviously, this is very skewed data and it's very difficult to make inference from here. But causal understanding allowed anti-smoking activists to still be able to say something concrete against smoking using a very skewed system. Now we'll try to understand how the actual graph helps us understand, helps us evaluate the causal effect of movement. So here we have a variable one. This is the genotype. Now, like I said, variables like genotype you can't really measure, so it's unmeasured. You cannot block that path. That is why we depend on our deposits in the first place. So we use this graph to evaluate the probability of the effect of smoking on us. Now what we see is that basically in this graph we can evaluate these problems. How can we do that? If we integrate things, then basically removing this variable, removing this arrow. And when you remove that, there is no other arrow to do. So you can evaluate the causal effect of X on W. And you can also evaluate the causal effect of W on Z. Because if you intervene on W, you remove this arrow, which again basically blocks up the work. So you can evaluate both of these problems here. So first we are evaluating X on W. And in this graph, we intervene on this, we remove that arrow. And yeah, so basically in this graph, it is the standard probability given of W given X. You don't need the condition because there is no other part. So there's only one part. So this will just give the standard condition probability. But if, in this scenario, we condition on W and the causal effect of W on Z can be written sum. Continue on exclusively because the causal pathway is actually blocked by X, so you basically need X to be able to find the probability because X was in fact confounded and you do have data. So we use that to claim that the probability of Z, given that you know the causal effect of X on Z can be written as a conditioned sum of interventions, two interventions. Now, why can we do this? So, if you're trying to find the intervening probability of X on Z, that means you're seeing your data, everyone is seeing that X, and you're finding the effect on Z. But this sum here tells you that you're fixing everyone at X, seeing what W is, and basically what we're saying here is the probability that you would fix everything at particular value of W can be represented as a conditional probability of W taking that value, given that X is fixed. Because you're trying to basically find the conditional probability of the X. And you can write this as this conditional term. And obviously, because we could integrate both of those, we can find in those formulas and we get this final answer, which is known as the front door equation. Formally stated, the front door criteria. So a set of variables is said to satisfy this if W intersects all directed points. Yeah.
Previous intervening on Z, actually you're continuing on the so the conditional name Y because that is the other variable is dependent on Z because
Y is not dependent on Z.
yeah, so sorry, not dependent. Z is the basically when you took the same intervening example in that case of the Simpson paradox, you said that Z is only dependent on one. So we take X, we condition on, in that case, X was in the middle. So we condition on X, and then we take all the values of Y and summation and do the summation from here. So
here it's summing over X because there is basically that was the backdoor part that was like pre-intervention. This was so pre-intervention. The backdoor part was from W X Y to Z, and that could be either of X or Y. But because we don't have data on Y, condition one won't help us. Condition one X is the only one that we can do. So condition one either of them works because the backward path is in fact blocked by X. Because X also had a change. Okay, makes sense. So, control right. So, set of variables satisfy the control if these variables, the variables in W, intersect all directed paths from X to Z, which means that the causal effect of X on Z is completely mediated by the variables in W. And there is no parallel path from X to W. So the association from X to W, as we saw here. There is no backward path. Obviously, there isn't because Z is a collider. So X and W, there is no open backward. That means the entire causal association is being transferred to W. And third point, all backward paths from W to Z are upward. So W isn't transmitting any other non-causal association. In this situation, W is completely mediating the causal effect on X and Z, and that is what is allowing us to write down this. So it doesn't matter that we do not have a variable we can measure. We'll still find out the loss. So that was about the calculus that I had to cover. So now we move on to complex. I mean, I will give a very brief work because it was not under the presentation. So complex calculus, again, like I was saying, we have two variables x and y. X is 1 if I use 2 umbrella and 0 if I do y is 1 if I do x is 0. So obviously two binary variables we have in these cases that might arise. But we use a counterfactual variable to improve on this. We call y sub x to represent the value of y under a certain value. So your y sub y would be 1 if, like say for example that if I was 1, so that is like 2 can number. So y sub 1 would be 1 if I took an umbrella and y sub 1 would be 0 if I took an umbrella and it didn't work. So use the variables y0 and y1 that we can represent our previous table like this. So what this means is at a particular given time, only one of x0 and x1 are actually occurring in. And the other this situation is called a counter. Because it is counter to the fact that it's happening. And what the counterfactual causal effect is defined as is the expected value of y, I don't mod 1 minus I represent that if x takes the value of y, mod 1 minus I will represent the other full thing. So here what it simply what means is that if I say took the umbrella and it rains, we want to find the what is the expected value of whether it rains or not if I did not take the umbrella. Given that it's real world, this is what I took the umbrella, it rained. So we want to find that if I did not take the umbrella, would it have? Now there are other tools that we use and find. They were a bit beyond science. So this is how counterfactual works, and that brings to the end. Thank you.
So, we will ask the observations. So, no questions. And thank you.